With the launch at lunchtime of the James Webb Space Telescope, a $10 billion project that has taken 30 years to reach this moment, humanity has entered a new era of discovery, as well as distant planets that could provide evidence of life beyond Earth. It now gives us breathtaking new views of our own cosmic neighborhood. Here's our science correspondent, Rebecca Morrell. The James Webb Space Telescope has once again expanded the boundaries of human perception by turning its immense gaze upon one of the most intriguing visitors to our cosmic neighborhood. Recently, it succeeded in capturing the first real high-resolution image of R2 Swan, a comet that has fascinated astronomers and sky watchers alike for decades, but has never before been observed in such clarity. The event was more than a technical triumph. It was a symbolic unveiling of how far human technology and curiosity have carried us into the depths of space. Before we start, hit the like and subscribe buttons for more exclusive news. R2 Swan is not a typical comet. Its highly unusual composition, complex chemical traces, and the peculiar brilliance of its coma and tail have puzzled scientists since it was first detected. Earlier telescopes, ground-based observatories, and even Hubble managed only to capture limited data because of the comet's faintness and erratic brightness. Webb's extraordinary infrared capabilities, however, pierce through layers of dust and gas to deliver a breathtakingly detailed portrait. For the first time, we could see the intricate structures within the coma, the swirls of molecular gas, and the exact texture of the nucleus itself, features that were once only guessed at or rendered in simulations. The unveiling of R2 Swan by Webb is monumental because comets are time capsules from the birth of the solar system. They carry within them frozen remnants of material that has remained unchanged for billions of years. By analyzing Webb's spectral data alongside the visual imagery, researchers have begun to map the comet's composition with unprecedented precision. They have detected water vapor and distinct jets, complex organic molecules woven through the coma, and an intricate interplay between frozen volatiles sublimating under the heat of the sun. These discoveries confirm that R2 Swan holds not only a wealth of chemistry, but also a deeper story about how solar systems evolve. The visual impact of Webb's capture is nothing short of stunning. Where once R2 Swan appeared as a faint smudge against the darkness of space, it now blazes forth in layers of radiant detail. The coma, glowing in hues invisible to the human eye, but translated into visible light, extends outward a veil of fire. The tail, stretching millions of kilometers, reveals braided patterns and faint secondary jets, each one a fingerprint of the physical processes unfolding within the comet. The nucleus itself, though tiny in comparison to its luminous shroud, emerges as a rugged, icy relic, scarred by countless journeys across interplanetary space. This kind of resolution was once unimaginable, but Webb's sensitivity has transformed a dim wanderer into a detailed object of study. The implications for planetary science are profound. By capturing R2 Swan in such detail, Webb has provided a model for future comet observations. Each new comet that enters the solar system can now be dissected with this same method, enabling researchers to build a comparative archive. Such a collection would illuminate differences in comet origins, reveal the various pathways comets take in their long orbits, and shed light on how they transport material across planetary systems. Already, some astronomers are suggesting that Webb's view of R2 Swan could be used as a benchmark against which to measure other comets. This single event may well mark the beginning of a new era in Cometary 1, defined by a standard of precision never before achieved. Beyond the technical and scientific outcomes, the cultural and philosophical implications are equally profound. Humanity has always looked to comets as omens, mysteries, or cosmic symbols. They appear suddenly, blaze for weeks or months, and vanish again into the abyss, reminding us of both the fragility and vastness of existence. The James Webb Space Telescope's image of R2 Swan is more than a scientific record. It is a modern myth, a new way of connecting the human imagination with the vast workings of the cosmos. The ancient fear of comets as harbingers of doom is replaced now by awe, curiosity, and wonder, fueled by the fact that we can see them as they truly are. What makes Webb's capture of R2 Swan so remarkable is also the timing. Humanity is on the brink of expanding deeper into the solar system with missions planned for the Moon, Mars, and beyond. Understanding comets is not merely academic. These icy wanders may one day serve as waypoints, sources of water, or even fuel depots for interplanetary travel. By learning their structure, composition, and behavior, we prepare for a future where encounters with comets are not just distant observations, but practical considerations for exploration. Webb's image therefore speaks both to our past and our future, revealing the primordial building blocks of our solar system, while pointing toward the era of human expansion into space. The scientific community has been quick to dive into the wealth of information encoded in the Webb image. Detailed spectrographs show a variety of volatiles outgassing from R2 Swan, including carbon monoxide, methane, and ethane, each a piece of the chemical puzzle that hints at the environment in which the comet formed. The presence of complex organics is particularly tantalizing as it strengthens the hypothesis that comets may have delivered prebiotic molecules to early Earth. If that is true, then comets like R2 Swan were not just visitors, they were couriers of the very chemistry that led to life. Webb's observation is not proof of this theory, but it gives it sharper definition, making the case more compelling than ever. For astronomers, the excitement also lies in Webb's ability to track the dynamic changes in R2 Swan over time. Comets are not static objects. They evolve as they approach the sun, jets flare, dust tails shift, and the balance of volatiles changes with every degree of solar heating. With Webb's sensitivity, these changes can be charted in exquisite detail. This allows scientists to model not just the structure of a comet, but its behavior in real time. R2 Swan transform under the heat of the sun gives us a living laboratory for processes that also shaped the early solar system. Every flicker of activity in the comet's jets is a clue to the delicate balance of ice, rock, and sunlight that governs cometary life. The visual data also serves as a powerful educational and inspirational tool for the public. Seeing R2 Swan through Webb's eyes is a reminder of what humanity can achieve when it reaches outward with curiosity. Students, artists, and everyday sky watchers can now look upon a comet not as an abstract, but as a detailed, vibrant world in miniature. The awe inspired by such imagery fuels interest in science, draws more minds into astronomy, and strengthens the shared sense that we are participants in a cosmic story much larger than ourselves.